Hi guys, so first I'm going to be giving you a recap of what was discussed in the previous video. So we mainly talked about the allotropes of carbon and the definition of the term allotropes, and we discussed diamond and graphite and their properties in detail. So now we're going to be discussing their differences. And the differences are going to be under two headings. So the first heading is going to be the difference in terms of their physical properties, and the second heading is going to be differences in terms of their structures. So the main thing over here is that the difference in their structure is what actually results in the difference in their physical properties. So for diamond, it consists of a giant covalent lattice, and it's the same thing for graphite. Graphite also has a giant covalent lattice, so this is one similarity between the two. However, in diamond, it's made up of tetrahedral units, and I've drawn the unit over here, and it was also discussed in detail in the previous video. And for graphite, it's made up of hexagonal units. So this is the unit which was also discussed in detail. The next difference is that in diamond, each carbon atom is covalently linked to 4 other carbon atoms, whereas in graphite, each carbon atom is going to be linked to 3 other carbon atoms. So in graphite over here, there's going to be many atoms that are bonded together. So if you look at this carbon, it's going to be bonded to 3 others. So the next allotrope of carbon that we're going to be talking about is Buckminster fullerene, also known as Buckyball, and the chemical formula for this is C60. Unlike diamond and graphite, this is not a giant molecular structure, it is simple molecular. And now we're going to be discussing this in a little bit more detail. So this is a hollow spherical structure of carbon atoms that are held in hexagonal and pentagonal rings. So over here, as you can see, this is a pentagonal ring because it has 5 sides. And this is a hexagonal ring because it has 6 sides. So it has various rings like this arranged in one circle. And each carbon atom is going to be bonded to 3 others. So if you look over here, this is one carbon atom and it's bonded to 3 others. There is some delocalization of electrons, and because of that, it's going to conduct electricity to an extent because there is only some delocalization. Now, Buckyball is going to sublime at 600 degrees Celsius, and the reason for this, it has weak van der Waals forces between the molecules. So if this is one molecule and you have another molecule next to it, the van der Waals forces between them are going to be weak, which is why it's going to sublime at 600 degrees Celsius. And another point is that it is somewhat soluble in non-polar solvents. So these were the general properties. Next we're going to move on to silicon dioxide, which is another macromolecule, and this is not an allotrope of carbon. So the first thing that we're going to be discussing is the arrangement of atoms. Now in this case, the formula for this is SiO2. And each silicon atom is covalently bonded to 4 oxygen atoms. In this case, the yellow circle represents silicon atoms, and this is bonded to 4 pink circles which represent oxygen atoms. So you can see that in the structure that I've drawn over here. The next point is that each oxygen is bonded to 2 silicons. So the oxygen is marked in yellow, and this is bonded to 2 of the red atoms which represent silicon. So each silicon atom is bonded to 4 oxygens, and each oxygen atom is bonded to 2 silicons, which is drawn over here. And basically, SAN is impure silicon dioxide. The next thing that we're going to be talking about is the properties of silicon dioxide. So the first property is that it has a high melting point, and this is because the atoms are going to be held together in a covalent lattice by strong covalent bonds. This is the main reason behind the high melting point, because a lot of energy is going to be needed to break these bonds. So because of that, it has a high melting point. The next property is that it has a non-conductor of electricity, and the reason for this, it does not have any free-moving delocalized electrons to be able to conduct electricity. And the last one is that it's hard, and the reason for that is the same as the reason for it having a high melting point, which is the strong covalent bonds. Now let's go and do a recap of every single thing that we've covered. So the first thing that we looked over was the definition of the term allotropes. Then we moved on to the differences between diamond and graphite, which are the 2 allotropes of carbon. And then we talked about Buckyball, which is the 3rd allotrope of carbon. And then we discussed the properties of silicon dioxide. So this was the topic of giant molecular compounds and the allotropes of carbon.